So let's take a look at the reactions of nitriles. First and foremost, our favorite reactions. In either the presence of aqueous acid or aqueous base, you can get your carboxylic acid out again. And we'll see both of these have an intermediate that is an amide. And as we know, amides under these same conditions also hydrolyze to carboxylic acids. So we'll kind of show the mechanism of how to form the amide. And then from there, the amide to carboxylic acid is the same hydrolysis that we saw last week. So we won't show that again. Let's take a look at the mechanism. So let's do the acid catalyzed hydrolysis first. The acid catalyzed mechanism here. We're going to go ahead and have our nitrogen attack our acid, which we'll say is H3O+. Because this is hydrolysis, you're definitely going to have water in there, so H2O will be your, or H3O+ will be your proton source. You'll have your protonated species now, which now our dear friend the water can attack. And I realize I've left her off. We open that up, giving us this oxime. That's not quite an oxime, but that's okay. We've got our water here. It's protonated. Just like with all of these acid catalyzed, base catalyzed things, we're going to have these intermediates that we just have to work with. So here comes another water molecule to grab the proton off, and it's going to transfer it in the next step to the amine. So we'll go ahead and stabilize our intermediate. All of these, by the way, are equilibrium steps. So we have now our OH, and the protonated water, the hydronium that we've just formed, is going to be used to protonate our nitrogen. So again, as before, we have all these proton transfers happening. That's pretty common when you're dealing with carbonyl compounds. We have now our nitrogen with its 2 protons on it. And if we go ahead and resonate this, we'll see how we're going to get our amide out. So resonance arrows here, we end up with the protonated carbonyl and the nitrogen there. And last step, our water comes in and will deprotonate our carbonyl, giving us the amide. And as we know, we'll have our sideways drawn amide. There it is. As we know, in a few more reactions, in the presence of that acid, this will become our carboxylate. So again, if you want to look at that mechanism, it's a good idea to practice it. Look at the mechanism for ester hydrolysis, or really any of the hydrolysis mechanisms that we covered as general mechanisms. That'll all be present there. So because it's the same reaction conditions, right? So you'll end up with your amide. That's the only new part, and then that amide gets hydrolyzed. And so that's our acid catalyzed mechanism. Protonate the nitrogen first. Nucleophilic attack by the water. Opens it up, forms that double bond to nitrogen, single bond to oxygen. Couple of proton transfers. And then we resonate, forming that protonated carbonyl of the amide. And then since we remember amides are not basic, we don't, we kind of see this form actually happening. And then we're going to have that water come in and deprotonate in our final step, causing us to get the amide. The amide is then continued in a hydrolysis pathway, allowing us to get back our carboxylic acid. And we'll get our ammonium. Ouch, since this is acidic conditions. Oops. We can take a look at the mechanism in basic conditions as well. So we're going to just avoid a lot of the proton transfer steps. So first thing first, in this case, is our nucleophilic attack. Opens up our carbonyl. We're going to produce water. And now we have the nitrogen that's negatively charged. It's going to go ahead and grab a proton off of the water that we just made. Remember, N- is a very strong base. So we will end up now forming our NH. We have our OH here. And our next step, we're going to go ahead and do some resonance here. And we're going to go ahead, not resonance, not yet. We're actually, because if we resonate right now, we're going to end up with positive charges, which we shouldn't see in an acid catalyzed mechanism. So we're going to actually deprotonate in the next step, and then we'll resonate afterwards, once we've formed it. So we'll have this deprotonation step happen. We'll end up with our alkoxide, which will now resonate inward onto the nitrogen. Again, this resonance is now a little bit less likely to happen because we're going to actually be forming a less stable form of it. But because this is all equilibrium, it's all just a matter of time before it gets there. So as this resonance happens, we end up getting our carbonyl, and we have our nitrogen now is negatively charged. It's got 2 lone pairs. And we're going to have our lovely water molecule around. And we're going to go ahead and grab a proton off of it, leading us to the product. So again, we'll regenerate our base catalyst here. And we're going to go ahead and have our amine, which will, as before, with many steps, will go ahead and turn into the carboxylic acid. That will be hydrolyzed as well. So take a look at the base catalyzed hydrolysis mechanism there. So very exciting things. We can hydrolyze them. Mechanisms are fairly similar to what we've seen so far, just slightly different, so that's why we showed them. A couple other things nitriles can do. So we can either turn them into carboxylic acids. That's great. We can do other things. Interestingly, with a Grignard, if we use a Grignard in the presence of our nitrile, let's say we use we can go ahead and have, I don't know, a cyclopentyl group. Why not? I'll have to switch that around because it's the other way. With the Grignard reagent, we actually get the ketone. Technically speaking, first, we end up with this nitrogen that is negatively charged once we've added on our whatever your Grignard happens to be. In this case, this cyclopentyl group. And notice that now, because this is negatively charged, it's going to kind of repel any more Grignards from attacking. We don't see more coming on. Because if another Grignard came along, we would end up with a nitrogen with a 2- charge, which is unheard of. We don't see that happening. So this does not react further, unlike with all the cases with oxygen present. We do not see this reacting further. And so in the presence of an acid workup, we'll end up with a ketone as a result. So you end up with your imine, and as we know, imines can hydrolyze to ketones, right? So double bond to nitrogen will end up hydrolyzing our imine, and we'll get our, in this case, we'll have the positive form of this, and so we'll end up with a ketone. So Grignards go through two steps. First step, the Grignard attacks. You end up with the negatively charged iminium, or iminial ion, I guess, anion, stabilized by the positive magnesium. Upon aqueous acid workup, that turns you into a carbonyl instead, and so you end up with the ketone. So, pretty useful. If you treat this with the dibol, you will get an aldehyde out. You'll need the acid wash on that too, I'm sorry. So, because you'll end up with the same idea. You'll end up with that negative nitrogen, which will then not be able to be attacked again, and then upon aqueous workup, it gets you the aldehyde. And finally, you can reduce the nitrile with the lithium aluminum hydride. And then doing so gives you an amine as well. So useful stuff here. With this, it's very similar to most of them, that if you take your carboxylic acid derivative, put it with lithium aluminum hydride, you'll end up with either the alcohol or the amine, depending on what you've got. Amides and nitriles reduce to amines. Everything else reduces to alcohols in the presence of the lithium aluminum hydride. And so that's it for our nitriles. So in our kind of last video here, we'll summarize all of the various reactions that we're seeing happening and what we can do with them, and how the ability to transform all of these functional groups into each other is enormously beneficial when you're considering synthesis.